Hey, so again, I'll remind you that the first midterm is Monday in class. The only thing you need to bring is a pencil, a pen, and a pinch. It'll be on a bubble sheet, 30 questions, multiple choice. And it'll be the same in many ways compared to past midterms, midterm ones. If you go far enough back, I only had one midterm, not two. But for the past 5 years or more, I've had 2 midterms. And so taking the old midterms is a good idea. People still wondering how to get access to them. They're on the page that I host myself on the cloud, the 1060.Bloomfield. Yeah. The password, it asks you for a password now to keep. And the password is, the username is Virginia, the password's physics, all lowercase. And it does tell you, remind you, you can find this on Colab, if you, those two. All right? So take the old exams, it's a good learning experience. From my perspective, it's, the point of this whole thing is to learn the material. From your perspective, of course, you want to get the highest score you can. I guess I should warn you, or tell you in advance, that the average score on this exam will be about a 70, probably 73%, 72%, which is fine. The point of it, I try to make all the questions reasonably challenging. I mean, they range, but there are no gimmies, there are no freebies that will boost the scores up into the 90s and stuff. So if those of you who have had long experience with tests that are scored 92% and above as an A and 84% and above as a B and so on, like, I can't do exams like that. That would be so treacherous. A single mistake would cost you. You could drop out of the A's by just misreading a question or me miswriting a question. So most students will miss a bunch of questions, and that's okay. I mean, it just is what it is. They're not trivial questions. All right? The grades will, the scores will range all the way from perfect scores down into the 1/4 score, 25%. It'll go the whole gamut. All right. Other questions about the exam structure and issues like that? Okay, a bunch of, I think today what I want to do, along with finishing how xerographic copiers / laser printers work, and starting a little bit into the world of flashlights, which is also the world of electric circuits. I want to sort of make sure I mopped up things I've left behind or that I need for those topics. And I'm going to go briefly all the way back to a question that showed up on a problem set. I've been asked it a number of times in office hours or before after class. And it's this question in concept. A gymnast, a diver, an object, a bowling pin, is falling. That is, it's not touching anything. It's in the air, which is kind of leave the air out of it, but it's not touching anything. Okay, the air messes stuff up. It pushes on stuff. There's air resistance that I'm not dealing with this semester. But when it's all by itself, what quantity does that object, the gymnast, let's say, have that's constant? And the quantities that are constant are likely to be conserved quantities, because all the other quantities tend to just vary at will. I can change my velocity all over the place, nobody cares. So my velocity isn't constant, it's easy to change. If something's going to be constant, it's probably going to be my momentum or my angular momentum. And the questions, all those questions, if you go back in the old exams and old homework assignments, this same kind of question will show up 100 times. Well, not really 100, but a dozen. And the idea is, so I throw some object in the air, what's constant about that motion? And it turns out the constant aspect is the angular momentum of the object about its own center of, its own natural pivot. It's rotating about a natural pivot, which is its center of mass. That is the natural pivot of objects. That it's a mass thing makes sense because that rotation doesn't have anything to do with gravity. You can go out in deep space and throw it and it'll spin about its center of mass too. It's an inertia thing. So it's going about its center of mass. And the question then is, okay, so does anything change its momentum and or its angular momentum? Well, there is something changing its momentum. What do you think is changing its momentum? What force is acting on it to do an impulse on it, transfer momentum to it? Gravity. It's weight. It's going from heading, in fact, it's going from heading upward with upward momentum to downward momentum. So gravity did a huge impulse on it, and that's the nature of things. Gravity is always doing downward impulses on everything. The reason that we don't notice that downward impulse usually is because we give away the momentum that gravity gives us. So I'm currently being given downward momentum by gravity. Every second I get my weight times 1 second in downward momentum. And okay, so why doesn't that cause trouble? Because I give it to the floor. So it's a whole loop. I give it back to the earth basically. So I'm not accumulating any. But if you take the floor out, suddenly I accumulate it and I'm in trouble. So for example, an airplane, if an airplane didn't have air to work with, gravity would give it downward momentum. How much? Every second it would get its weight times 1 second's worth of downward momentum, and it would accumulate it, and that would be that. Fortunately, it has air to work with. And if you want to boil down airplane flight into one simple observation, the job of the airplane's wings is to give away all of the momentum that gravity gave to the airplane. So the gravity gives it downward momentum to the airplane gives downward momentum to the passing air. And the air is actually left heading downward because it's got downward momentum. All right, that's so far. So the momentum of an object that is falling is definitely not constant. It's exchanging momentum with the earth by way of gravity. That leaves one other thing to look at, which is angular momentum. Does the object's angular momentum about its natural pivot change, about its center of mass? And interestingly enough, the answer is no. Gravity does pull down on the object, and that could conceivably twist the object, but it doesn't. And the reason it doesn't is because gravity effectively acts at what we call the center of gravity. So if you want to distill down, where is the weight of this wacky mallet located? It's located in a point right about in here, the center of gravity. So in many simplified contexts, you can simplify this complicated shaped object as though it were a single little nugget at the center of gravity being pulled down. So gravity is pulling it down at its center of gravity while this thing is rotating about its center of mass. And the wonderful thing about this relationship between mass and weight near the surface of the earth, that every kilogram of mass develops 9.8 newtons of weight. It means that the location of the center of gravity of this object is at the same point in space as the location of the center of mass of this object. They coincide. That's true of any object here near the surface of the earth, any modest size object near the surface of the earth. And why do I have to put those waffle words in there? It's because the object's got to be small enough that gravity doesn't vary over the size of the object. If we talk instead about something that's huge, like the moon's center of gravity and its center of mass are not quite the same location because the Earth's gravity varies over this gigantic ball. Earth's gravity is stronger on the near side of the moon than on the far side of the moon, and that messes everything up. But here near the surface of the Earth, objects, basically their center of gravity and center of mass, despite being different concepts, are located at the same location. What does this do for us? It means that gravity yanks down on the object right at its natural pivot, and you can't twist something by yanking on it at the natural pivot. It's got no lever arm. It's like trying to open a door by pushing at the hinges. You can't do it. So gravity doesn't yank anything at its center of mass, and therefore doesn't twist anything. And what implications does this have for falling objects, which often include people? I'm not in a bad way, but like divers, acrobats, gymnasts. Anytime you've gone, you leave the ground, your angular momentum is stuck. You can't change it because there's nothing apart from air effects, which are not trivial, they're minor. Nothing's twisting you, and therefore if you've got angular momentum, you keep it. Same amount, same rotational axis, you can't vary it. For divers, this is a big deal. All the somersaults and stuff that they do in dives, they've got to be very careful in dealing with their angular momentum. Yeah?
I have a question about lift.
Yep.
So when there's a falling object and there's the force in the direction that it's traveling,
Yes.
what is working on you? Is it the earth?
So when an object is falling and there's a downward force,
Yeah.
what is working on you? The Earth is taking energy that was stored in the force of gravity, and it is transforming that as you fall into kinetic energy in you, because gravity is pulling you down as you move down. It's in effect transferring energy into you. We already kind of assigned that energy to you as your gravitational potential energy. So you had it already in your accounting ledger, 1,000 units of gravitational potential energy, even though it's actually stored between the two of you. And once you start falling, it moves out of the ledger as potential and becomes kinetic in you. Unless, of course, we lower you on a string and let you run an electric generator, in which case it doesn't become kinetic necessarily. It can go out that you do work on the string and you give the energy to the generator, which sends off the energy elsewhere. Is that okay? So things that are falling or midair, they rotate in interesting ways that are often dominated by angular momentum. And you can watch this in everyday life. It shows up in all kinds of sports, high jump, long jump. People jump. You can't just like jump, rotate sideways, and then stop rotating to go over the bar or something like that. You can't do it. Once you leave the ground, angular momentum is stuck. All right. Any questions about that? Other things that came along here, questions that people asked about. To revisit the idea of voltage, which surely takes a bunch of visits. So voltage measures, is a property of a location in space, and it tells you how much energy each unit of electric charge has stored at that location, if it were at that location in space. Or alternatively, how much in fact, it's electrostatic potential energy, energy associated with electric charges. How much work would one unit of electric charge do on you as it left that location? And you might think, well, this sounds all very vague and strange, but you have seen similar things in more tangible contexts, like the energy per kilogram that comes with being up high. It's gravitational potential energy, but certainly a box full of bowling balls at the top of a hill have a lot more stored energy than a box full of bowling balls at the bottom. So one way of sort of thinking about, well, it's kind of altitude and gravitational potential energy. Altitude measures how much energy per bowling ball you have stored in gravitational potential energy. And you measure it by seeing how much work one of those bowling balls will do on you as you let it down off to the average height, the zero height. Pressure, water pressure, same idea. Water pressure measures the amount of energy per unit of water, a liter or a drop. And at high pressure, you got a lot of energy per drop. It can do stuff, it can do work. And you can measure the pressure in effect. In fact, you really can measure the pressure of water by how much work it'll do in going from high pressure that you're worried about to zero pressure, the zero pressure. So that's just, I don't want to dwell too long on the analogies. I'll just get you mired in them. I'll get mired in them. So go back to voltage. If you look at the voltage of a particular location in space, so I'll pick one. And what I'm going to pick is a high tension wire that we'll imagine is running through the top of the classroom. And I'm going to tell you in advance that that's a 100,000 volts, positive 100,000 volts up there. And that's not uncommon at all. You can find power lines around Charlottesville that if we look at one instant in time, it will have that all along that wire, it'll be 100,000 volts up there. What does that mean? It means that if we go up to that line somehow safely up there and we obtain one unit of electric charge, again, the unit of electric charge is the coulomb. Take 1 unit of electric charge and begin to take it away from the power line. We'll discover very quickly that it's happy to leave, it's pushed away. And in fact, it just does work on us as we carry it away. We'll feel the repulsion, and it will do work on us. And by the time we get off into far, far away land, it will have done 100,000 joules of work on us. And that's the origin of the title, or the idea that it's 100,000 volts. If it were only 50,000 volts, it would do only 50,000 joules of work on us in leaving. The forces would be a little weaker. In fact, they'd be about half all the way along. All right? Yeah. Does it become more intense as you get? It's most intense when you're close, okay? Because like charges, as we've seen charges, the forces between charges are strongest when you're near them. So there's an interesting, this is a good question, because of what it says. So we're going to leave that 100,000 volt wire, and we're going to go farther and farther away, and it's going to do less and less work because the forces are getting weaker. In reality, yes, it's 100,000 volts. Where did that come from? There's a lot of positive charge on the wire. And we could calculate what it is. It's a hard work, but you can calculate how much positive charge is sitting on that wire so that as this unit of electric charge leaves, 100,000 joules of work are done on it. And this would be a perfectly good question for, well, probably a physics major in one of their later classes. It's too much, it's enough, okay? That does bring up the idea, and this is why the question is so intriguing to me, is what happened if we go near the wire but not at the wire? It's true there's nothing there, but it still has a voltage. And if we go, so here's the wire, and we'll start here. And we'll take our hypothetical 1 unit of charge and let it do work on us. Well, it's not going to do the whole 100,000 joules, right? Because we lost the juiciest part of the push. So we're starting here. That might be 50,000 volts. And that would be the voltage of that location in space. It's empty, nothing's there, but it has a voltage. And the voltage might be 50,000 volts. And you get a little farther, now it's down to 25,000. And now it's down to 10, 3, and into the dust. And for a wire at high voltage, the voltage will fall off pretty fast as you leave the wire. And one way to think about this, just conceptually, is that if you're flying around your butterfly up there, and when you're near the wire, you see it looks pretty big. It's a big cord going by, and it takes up a good fraction of your field of view. And you look at that, and you look at the world around you, and you say, well, in fact, this thing's 100,000 volts. The world off in the distance is 0. And the Earth is pretty much at 0 volts. And this is getting a good bit of my attention, but not all of it. So the voltage where you are, you the butterfly, is some compromise between maybe 10% that 100,000 volts and 90% the rest of the world, which subtends most of your view. So the voltage falls off as you sort of lose the ability to see that wire, which is pretty fast. So the voltage plummets as you leave the vicinity of the wire. If it weren't a wire, but rather a sheet, a plate, a surface, as you leave it, you'd still see a lot of it. It subtends a lot of your view, and it continues to subtend your view, particularly if that plate goes off vastly in both, up and down, left and right. And so the voltage doesn't fall off as fast. You have to get farther away before that becomes sort of a trivial part of your field of view. The most extreme case is, what if instead of having not a surface, which really is the voltage from a surface falls off slowly. The voltage from a wire falls off a lot faster. The voltage from a pin, and this is why I'm saying it, you guys, some of you have taken the most recent of the midterms, encountered a question that talks about a pin. If you leave a pin, if you're up really close, you butterfly up there and you see, oh, there's the tip of that pin, and it's subtending some chunk of my field of view, but boy, the world looks a lot bigger to me. The voltage falls off dramatically fast from a pin. That is, you don't have to get very far. If the pin has got a tip that's 1/100 of an inch in diameter, you get 1 inch away and the pin is nothing It's just, it's a mere speck in the distance. So the voltage just plummets from a pin. Yeah. Lee? You know, so when we talk about a positive charge, when we talk about taking a charge away, the word positive is implicit. And conceptually, I'm thinking of what's called a test charge, which is always positive. The fact that I use the word charge without a modifier in front of it already implies it's positive. This is actually a special charge. It's a test charge. Why? What's a test charge? It's a version of charge that doesn't influence what it's leaving. If I actually went up to the wire and grabbed 1 full coulomb of real charge, it would mess the wire up, because now it would be pushing on all the charges in the wire. And that'll just, it disturbs the story. So we pretend it doesn't have any effect. And then we take it away. So it's a test charge, meaning it doesn't affect the wire, and it's positive. And if you take negative charge away, all the signs will go backward, go upside down. Things will become negative here and there, and you get all confused. So we physicists and engineers mostly stick with positive charge in everything they do, unless they absolutely have to go and look and see. They're working actually with a negative charge. Is that okay? Okay, sure. Okay. Let me try to. I think I understand your question. I'll give it a shot. We had a 100,000 volt wire running through the room, and I told you that a coulomb of test charge, a non-disturbing charge, will get an entire 100,000 joules of work done going off into the different distance. And then I also said that if you start a little, you don't actually start at the wire, you start a little away from the wire, you get less energy per unit of charge because the voltage is decreasing. It's 100,000 on the wire, it's less as you go farther from the wire. And the details, let's not worry about it. What if you got a second wire over here that's minus 100,000 volts? Is that okay? That guy's going to be covered with negative charge, a lot of negative charge. And if we go and we get 100,000 units of test charge up there, not 100,000, 1 unit of test charge up there, it's going to be very unhappy leaving. I'm going to have to drag it out of there. I'm going to have to pull it away from that charge because its test charge is positive and it's leaving a negatively charged thingy. So I have to drag it the whole way. And by the time I get off into the far, far away land, I will have done 100,000 joules of work on the charge. It's a total loser for me. That means instead of being positive 100,000 volts like this guy, it's negative 100,000 volts. Is that okay? And so I've got 2 wires, one at plus 100,000 volts, which in fact has lots of positive charge on it. Physicists sort of forget to tell you that. It's easy to just say, oh, it's on plus 100,000 volts. Kind of like, so why? Well, because it's covered with the positive charge. And the negative 100,000 volt one, which is covered with negative charge. If I go and I grab 1 unit of test charge at the 100,000 plus wire and carry it to the 100,000 minus, it'll do 200,000 joules of work on me. So this is the concept that we use in electric power distribution, whether it's power lines or whether it's batteries or any of that stuff. What you're generally doing if you are a consumer of electric power is you are taking charge from the positive wire, the wire with positive voltage. You're taking charge, letting it do work on you as it leaves, and letting it do more work on you as it goes to the negative wire. And that work might be an electric motor, or it might be an electric heater. And the charge goes from one wire to the other. You don't keep the charge, but you keep the energy. So electric power distribution, I mean, the reason why all these electric outlets that you've ever encountered have at least 2 wires, There are no electric outlets that are just one wire. They're all 2 wires. In fact, most modern ones are 3 wires. The third wire is a safety feature. It is electrically connected to the ground, literally the dirt. And the earth is not a great conductor of electricity. I mean, just dirt isn't a great conductor of electricity, but it's good enough. And so connecting that to the ground is a safety feature, meaning that if you touch that, if you or anything touches that ground wire, any charge that's around will go rushing into the earth and spread out all over the whole earth. Gone. But okay, so setting aside the ground wire, which incidentally is the big round pin on U.S. outlets, the two flat wires most of the time differ in voltage. The details we'll come to because it's complicated for reasons that date back to the commercial battle between Thomas Edison, who wanted to deliver electric power with what's called direct current, and George Westinghouse and Nikola Tesla, who wanted to deliver electric power as alternating current. The reasons for that are in our future. You know, why one versus the other? Tesla and Westinghouse won. We have an alternating electric power grid here in the United States and the whole world. That may change in your lifetime. We'll see. But why in the diversion? It's because my little story of there's a power line up there that's plus 100,000 volts, and there's one that's minus 100,000 volts. We had to do that at one moment in time because the power lines around us are typically not at steady voltage. The voltages are changing with time in an interesting way, and we can only take a sort of flash photograph of them and say, right now, 100,000, minus 100. The same is true of the electric power outlets. Which wire is the higher voltage, which wire is the lower voltage? It depends on when you look and which wires you're paying attention to. But the point is that all the devices you plug into the electric power outlet, they receive charge at high voltage, suck the energy out of it, and return it at low voltage. So it goes back with less energy per charge. And the missing energy per charge, where does it go? It's what makes your computer work, your light bulb light, your toaster toast. And so the rest is all just details, but that's the basic concept. Is that okay? Yeah, I think I've pretty much covered these. If not, ask me again. But I now want to go. So I've talked about charge, the forces between charges. I've talked about the energy that can be stored in the forces between charges, as measured typically by voltage. So voltage measures the energy per unit of charge. It's rarely interesting to say how much total energy does the charge on that ball have. I mean, it has some value, but who cares? More interesting is how much energy it has per charge, per unit of charge, and that's in the vicinity of minus 100,000 volts. That guy gets negatively charged. Let me show you one more thing that I certainly left behind me, and that is this. I showed you that we can charge stuff by bringing into contact two dissimilar materials. They will chemically fight over charge, particularly electrons, unequally. And when you separate the two dissimilar materials, almost for sure you're going to have, one of them is going to have more electrons on it than the other. And the result is the one that with extra electrons is going to be negatively charged. And since charge is conserved, if you started with two neutral objects, there's no zero charge to work with, grand total. If you pull off a negatively charged piece, the other side's got to be equally charged but positive. So when you pull things apart, so this happens when you separate two objects. They're typically neutral before you separate. When you separate them, there's a very good chance one will be positively charged, one will be negatively charged, and they will therefore love to stick together subsequently down the road. All right? I showed you can do that. I showed you that opposite charges attract each other, and I showed you that if you just got a charged thing like a balloon, and you bring it up to an electrically neutral thing, it will still stick. And that's true of regardless of what the neutral thing is. It can be an insulator, it can be a metal conductor, doesn't matter. As you bring the charge balloon up, you will move charges around in the neutral thing in such a way that there will be an attractive force. That moving around charge is just called generically polarization, and it is just easy to make happen. There is a cute trick you can do with that polarization effect. If I bring a balloon up to the wall's an insulator, the movement of charge in the wall is so dinky we never really notice it. But if I bring the balloon up to a piece of metal, the polarization can be significant. What happens is if I bring a negatively charged balloon up to a piece of metal, I will attract positive charge onto the near side of the metal. Metals allow charge to move. So if I bring my negatively charged balloon up to the metal, it's going to bring positive charge all the way right up to stare across this empty space or air at that balloon. It loves it. Meanwhile, negative charge on the metal will leave as far as it can go. If it can go to the back side of the piece of metal, it's pretty happy. If the metal is touching the earth, that negative charge will actually leave, and at least in concept, will go to the other side of the earth. So you polarize the entire earth if it's conducting. So what happens if you take a piece of metal that's connected to the earth, you polarize it by bringing up a charged balloon, you pull positive charge onto the piece of metal, you send negative charge out a wire all the way to the other side of the earth, and now somebody cuts the wire. If you do that, you trap the positive charge on the piece of metal and the negative charge on the far side of the earth. They can't get back together again. And that charge on the piece of metal, the positive charge that you've produced on it, is real, and you can see it. And this is called polarizing, charging by induction. And I'll show it to you. And the way I'm going to do it, just for fun and games here, is I'm going to be the conducting object. I'm not metal entirely. We're actually pretty good conductors inside our body. Our skin is good insulators, which is very helpful. It saves us from a lot of trouble. But in this story, I'm going to be a pretty good conductor. And the ground and everything, I'm well enough connected to the ground and the whole world that I'm basically metal touching the whole earth. But when I step on that plastic stool, I will break the connection. So what I'm going to do is I'm going to suck positive charge. I'm going to turn on the gadget, the Van de Graaff. It's going to cover itself with negative charge. When I get near it, positive charge is going to come up onto me, onto my hands, onto my head, and be drawn towards that negative charge. I'm going to be covered with positive charge. And the charge is going to come up through the ground onto me. And negative charge that used to be on me, some of it, is going to leave me and go over to the far side of the earth. If I just then walk away, it'll all go back to normal. The positive charge on me and the negative charge at the far side of the earth, they'll get back together and the whole story will be boring. But if I step onto the stool, the charge can't get back together. I've got positive charge trapped on me, and I'll show it to you. Okay? So to show it to you, to start initially, I don't have any charge on me. Oh, I just banged it. I didn't make it. See, no charge. Is that okay? Let me turn this guy on. I'm not going to let it zap me. That's just, that's a different story. I'm going to let it pull positive charge onto my hand. Negative charge is left. It's gone over far, far away. And now I'm going to insulate myself. I'm now standing on the stool. But the positive charge that was pulled onto me by the Van de Graaff generator, it's still there. There it is. Come back here. It's real. If I let it go back into the earth, gone. Right? So I left some on there. As soon as I get near there, I get polarized. I have to let it suck positive charge onto me. Now I'm covered with charge. Okay? There are other ways of demonstrating it that are maybe a little bit more convincing, but they don't involve me. I get tired of getting lightning bolts all the time. All right? So that's a notion called charging by induction. It happens. It does happen in the real life pretty easily too. If you bring conducting things near something that's electrically charged, they end up with charge on them, and it's very easy to end up with leaving the charge on them. Okay. Before we get too far along here, I want to discuss electric fields, which I've just left behind, but it's very important. The reason electric fields are important are, well, for the zero gravity copier and laser printer, they are the way in which they underlie the technique that's used to spray charge out onto the photoconductor surface. But we're going to be using electric fields for a long time, and so let me try to give you an idea of how they work. So here's the intro to electric fields, which is just jargon gibberish at the moment. Let me just build up to what the heck is an electric field. Two positive charges. Based on everything I've shown you up until this point, we know that these two guys push apart. They repel each other like charges. And the forces between them get stronger as they get closer. And it happens to be an inverse square law, so that this is a very strong force. This is double the separation. We get a quarter the force, and so on. Well, and I can bring in negative charges, and we can do the whole fun and game again. What about if we create this intermediary that's at least initially looks like a total wasted activity, like why bother? What about saying that this positive charge dresses itself, envelops itself in some structure in space that in turn pushes on this electric charge? So that rather than having this charge push directly on the red charge push directly on the blue charge, what if the red charge builds something around itself, carries it around with it? Decoration. And that decoration does the pushing. Okay, seems like a total waste of time. Why would we do this? Well, let me sort of illustrate what that looks like. That decoration looks like. I'm going to put the red positive charge, the one that's creating the something around it, and let's say that if I put the positive charge here, it feels a force to the left that happens to be quite strong because the two charges are pretty strong there. So let me say that there's something here at this location in space, marked by the dot, that pushes to the left, that will push positive charge. Again, will push charge, because charge is implicitly positive unless others said otherwise. It will push charge to the left. How about if we go down here? Well, in this case, at this location, the push is downward. At this location, the push is rightward, and so on, upward, right? If I get farther away, it's still to the left over here, but it's not as strong. If I go farther, it gets weaker still. And so on there. So this thing at each location in space gets weaker and weaker with distance. But it's always pointing away, directly away from the positive charge. And you can do it in the middle. It's down this way, and so on. You can just keep on mapping out all the directions. Well, what I have just drawn for you, and actually, and there's in front and behind, but I'm running out of chalkboard front and behind. What I'm mapping out is a structure in space that consists of a vector at every point in space. There's a vector here. Its direction tells you which way positive charge is pushed, and its length tells you how hard the positive charge is pushed. So you can go nuts with this, and in the animations associated with the book, I did go nuts. This whole structure is this elaborate lattice work of vectors all pointing away from the positive charge. Well, that structure in space seems like a fiction that like, why bother? It's given a name. It's called an electric field. And the why bother is answered by the fact that it's real. It's not a fiction. Electric fields are actually there. And they're very important. And they can have a life of their own even without charge, which is going to be, it's in our future too. But as a hint of this, let me say that this positive charge sitting over here feels a force to the left that is designated by that left pointing arrow that's of modest length, because we're getting kind of far from the positive charge. This charge is feeling a push to the left, and you might think, well, it's not really being pushed by the thing that's right there, that electric field. It's being pushed by the red charge, and we just made a fancy way of saying that. But it turns out that if I take that red positive charge and I move it very suddenly, I rip it right off the board, for example, it takes a little while before the blue charge notices anything changed. So I can just steal the red charge. I can't quite rip it like clean off to the moon, but for good reasons. But I took it away, ha ha ha, and the blue charge doesn't notice for a while. The structure in space survives for a little while without the red charge. You might wonder, okay, how long does it take before the blue charge notices something changed? The information about the change travels at a particular speed, one you've heard about your whole life, the speed of light. So it's not a long wait. This is about a foot. It takes about a nanosecond, but the blue charge will not know anything happened for a nanosecond. All right, so electric fields are real. They'll get more real as time goes on. We'll discover ways of making them and having them move around without any electric charge. All right, how about the electric field around a negative charge? It just points the other way. So here's the negative charge. Oh, I lost my sticky. Anyway. Oh, come on, stay stuck. There. Okay. Electric field, again, it tells you which way a positive charge is pushed. Now it's toward the negative charge. And very strong when you're up close. And gets weaker with distance. And if I had a positive charge and a negative charge, the two work together to make electric fields, so you get these complicated shapes and structures, which we could spend ages dealing with, but it's not worth it. Okay, so that's the basic introduction to the electric field. It initially shows up as an intermediate between one charge and another charge, a way that charge A influences charge B. Incidentally, charge B, of course, creates its own electric field, which then influences charge A. And what a test charge doesn't do, what distinguishes the test charge, which is a concept, it's not a reality. A test charge creates no electric field. It just observes everybody else's electric field. That's what makes it special. It doesn't muck up the world around it. So why is the electric field important in this particular, why bring it up now? Looking at zero-graphic copiers, they do manage to spray electric charge onto a surface by getting the air to ferry that charge from a point or a thin wire to the surface. Now, why would that work? Well, if you look at the electric field around a point, if I put 1,000 plus 1,000 volts on this knitting needle, it's going to be covered with positive charge. That's finally underlying how it manages to be at 1,000 volts. Those charges are going to be spread out along this knitting needle pretty uniformly, except at the tip. At the tip, each charge, the charges are trying to minimize their individually their total potential energy. If they can go somewhere that reduces their potential energy further, they will feel forces in that direction, and they will accelerate that way. So when the dust settles and everybody's settled down and happy at equilibrium, the ones near the tip have had a conflict. They see all these positive charges along the wire, and they want to get away from those. So that means go toward the tip. On the other hand, they also see a lot of positive charges right at the tip, and they want to be away from them. And they can't make up their mind. And what they do is actually they pile an awful lot of them right on the tip. So at the tip of the needle, when it's the whole thing's at 1,000 volts, there are an awful lot of positive charges right there on the tip, an unusually large collection. And what that does is it creates a very strong electric field right there. The positive charge is all packed very tightly, and if it's positively charged, the electric field points away from it, and it falls off quickly. The electric field is very strong right near the tip, and it plummets as you go farther away from it. And I guess I can draw this too, since I've already broken the ice on the chalkboard here, to mix my metaphors. All right, so here's the needle at 1,000 volts. There's a very strong electric field right here, pointing away. It gets weaker in a hurry. And so there are two things that are sort of interesting to notice. Is 1,000 volts means that if I take a coulomb, a unit of charge, and let it walk away to infinity, it will do it'll do 1,000 joules of work on me. But almost all of that work will be done in the first millimeter leaving the tip, because that's where the push is strong and the work is big. Once I get very far away, there's not much energy left. And in fact, what that also means is the voltage plummets as you leave that point, which is something I told you earlier in this hour. The voltage is 100,000 volts on the tip, but you go a millimeter away and the voltage is down almost to zero, because all the push, all the force involved in doing work on me, it's all right near the tip. There's nothing left out here a millimeter away. So, just to say it because of the time, if this is 100,000 volts, it's 100,000 volts, right around the tip there's going to be a tremendous electric field, and the voltage is going to plummet from 1,000 volts to almost zero by the time we got it here. And together, that's going to push charge off the tip onto passing air molecules. Once they're out there, they look toward the tip and they say, they're going to be positively charged. They're going to look back to the tip and say, no, 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 it's positively charged too. I hate that. It's going to look at the surface and say, I'll go there. It's negatively charged. This is good. And I can do the same process. That leaving process is known as a corona discharge. It's different from, if I put my hand out here and play knuckles with this, the electric field's kind of uniform between me and the ball. I'm not quite the same size as the ball, but we're very close. And so if that's minus 100,000 volts, I'm going to be about plus 100,000 volts. It's going to fall off uniformly. The charge is going to be pushed sort of uniformly wherever it is in the path. And the electric field, there will be an electric field there. It'll be pretty uniform, and it will get stronger and stronger as I get closer until finally the air can't stand it. If you put air in a strong electric field, you begin to pull apart its positive and negative pieces and cause a lightning bolt. So the lightning bolts that come here, the electric field is so strong in this area that it is ripping apart air with a little help from cosmic ray charged particles. This is a longer story than necessary, but the result is a catastrophe. Once the air has begun to fill up with charged fragments, electric charge can shuttle by using those fragments. So that the spark is filled with charged particles. That glowing thing, it's full of air fragments. Not so if I go up with a pin. If I go up with a pin towards that ball, it's minus 100,000 volts. It has pulled a whole lot of positive charge onto the tip of the pin and created tremendous electric field right at the tip of the pin. The field's so big that it is pushing positive charges right out of the tip and onto passing air molecules. They're now positively charged air particles, and they are attracted to the ball. They love it. They go over there. So I'm literally spraying the ball with positive charges right now. No lightning bolt. If too many charges flow, the effective tip of the pin gets bigger because you see the tip, but if it's pouring positive charges into the air, the air near the tip starts to count as positive charged stuff. so the tip sort of gets too big. And the electric field gets smaller, the effect goes away. So it's self-regulating. And the result is that I can discharge the ball without any lightning bolts. No problem. This is the concept behind lightning rods, sorry. Too many bolts. When Ben Franklin may not have understood exactly what he was doing with lightning rods, but he had exactly the right idea. The purpose of lightning rods is not to have a pin on the top of your house that gets hit by lightning instead of the rest of your house. I mean, okay, that's decent protection, but not ideal. You don't really want lightning to come anywhere near you. So rather than sort of putting a sacrificial widget on top of your house, what you're really doing is you're putting a pin that sprays opposite charge toward the charged clouds overhead. So suppose some great big positively charged cloud comes cruising over your house and all your neighbors. What all of you guys are doing is that pin, you've got a pin pointing up, spraying, it's a positively charged cloud, so negative charge goes on the pin, does the corona discharge trick, makes negatively charged air particles that go up to the cloud and wipe out its positive charge. So if you get a whole community going with lightning rods, there's no lightning. You discharge the clouds. His problem back 200 years ago was trying to convince more than one person to do it. The first person who did it still got hit by lightning. You wanted to get the whole community going, and it was a big battle, but eventually now we're like that. Houses typically now have lightning protection that discharges the clouds. All right, see you on Monday for the exam.